Hello and welcome to this tutorial on pyelmer. In this video I'm going to show you an example from Crystal Growth, which is this small demo setup which we use to grow thin crystals. The simulation that I'm going to show you will consist out of this crucible, which is filled with liquid tin, and the crystal that is growing out of the melt. I'm going to simulate this in a steady state two-dimensional case with a heating at the bottom and a cooling through heat conduction and radiation at the surface modeled by heat transfer coefficient and idealized radiation. Here I already prepared the code for this case. Here I import different things. From pyelmer I'm using the same stuff as in the last video, and most important, I import from the Gmesh module the model shape objects that help me to set up the geometry. Here I just set up my working directory. That's where the parameters for the geometry are stored so that I can modify them easily later. And here I create the model object. This model object is used on the one hand to initialize Gmesh. On the other hand, it's a container that stores all geometry parameters. The geometry is in my system represented by shape objects that are created for each body. It can be anything 2D, 3D, 1D. And here you see the parameters. It gets the model where the shape is added to, the dimension in name, and then the Gmesh geometry IDs. And to create my crystal, which is just a rectangle, I use this Gmesh command add rectangle with the origin and the size of the rectangle. For the melt it's the same, it's again just another rectangle. The crucible here is a bit more complicated. I have two rectangles, one is the main body, the other one the hole, and then I cut this hole into the main body. And again then I create a shape object. I need to set the connections between the different shapes. I can just easily do this here by using the set interface function of the shape objects. Crystal.set interface to melt, so crystal knows melt, and melt has a connection to the crucible. That's why I here call this function again. So for the boundaries, the shape object have some nice functions that I can use to access them. For example, for the crystal, which is a simple rectangular object, I can use the crystal top boundary, which is just a property of the shape object, and returns the ID of the top boundary of the crystal. In my case, I need the top and right boundary and use those to create a new shape. The same I do for the melt with a different function with a boundary in a box, and for the crucible surface. Then at the interface between the crystal and the melt, I use another function. I can also just access this interface directly by asking the crystal for the interface to the melt shape. Now let's have a look at this model. Here I just create the physical groups and I run this script. It looks like this. The crucible is here, the melt and the crystal, and by visualizing the different physical bodies you see the bodies and the boundaries and interfaces that I just defined. Everything looks correct, so we can continue. In this case I want to create a better mesh, and for this I use my mesh control my mesh control classes. Here I set a constant mesh size in the crucible and the melt of 5 millimeters and of 0.25 in the crystal, which then looks like this. It's okay, but I want to have a higher resolution here at the interface between the melt and the crystal, which is important in crystal growth. And that's why I can remove this, it comes later. That's why I add here in exponential mesh control, add this interface with a mesh size of 1 millimeter it is, and yeah, exponentially increasing, and it is applied to the crystal, to the melt, and the crucible. Here I then generate a mesh, I visualize it, and write it to my simulation directory. Here you see this exponential mesh size constraint. Okay, then going to the pyelmer part. For the Elmer setup, I load my axisymmetric simulation. The materials I can load again, but I need to change some of the properties to stay consistent with some other assumptions that I did previously. That's why I need to update my data dictionary with the new emissivity, for example. Yeah, the solvers I load just again the heat solver and the result output solver, and the equation that I'm using here, it's just one consists out of the heat equation, the heat solver, sorry. Then I add my bodies with the different materials, the boundaries with a fixed heat flux at the bottom, again a fixed heat flux at the crystal melt interface, which is the energy released by the crystallization, and at the surfaces I set on the one hand the fixed heat transfer coefficients to model the conductive cooling by the air and idealized radiation. Yeah, now I just write my zip file, run my simulation, and scan the log files, print the errors warning and statistics, which was already done here in the previous one. And then we can look at the result. So this is the temperature distribution inside our crucible, the melt, and the crystal on top, which has here the melting point, and that's just the result I expected. Thank you for watching this video.